So often, right, we have to measure quantities, right? And like when you're driving, you measure your speed. When you need to find a length, a height, you measure that. And usually we have numerical quantities for these, right? So I'm driving at 65 miles an hour. My height is, 5 feet and 7 inches, and so on. Now, those are all quantities. They're called scalar quantities. A vector, however, is a quantity that has both magnitude and direction. So it's one thing to say I'm driving at 65 miles per hour. And then it's another thing to say I'm driving at 65 miles per hour east. Now you've given two pieces of information, a magnitude and a direction. And those are called vectors. Examples of vector quantities are velocity, like I just talked about, force, right? So you can say there is a force on this object of 5 newtons applied in the downward direction. That is a vector quantity. So, like I mentioned, a quantity with only a magnitude and no direction is called a scalar. So scalars are just, 3 miles, 27 newtons, 5 miles an hour. Those are scalars. All right, so as I mentioned, the velocity of an object would be 6 meters per second east, but its speed will only be 6 meters per second. So the velocity is a vector quantity, but the speed is a scalar quantity, right? And so if we go down here, you have a situation here where a ball is thrown northwest at 60 meters per second. Is that a vector or a scalar quantity? That's a vector. How about a tennis ball served at 110 miles an hour? Scalar. And the sprinter running 100 meters north? That's a vector. All right? Now, because vectors have a direction, and that direction doesn't necessarily have to be up, down, left, right? It could have any angle. The best way to represent them are with what we call an arrow diagram or a directed line segment, because we got to get fancy. So take a look at the vector here, right? You see that it looks very much like a ray that you've learned about in geometry. It has an end point, and then it has an arrow on the other end. Okay. Now, the end point, that's the initial point. That's the starting point. It's called either the initial point or the tail. The second point, the terminal point, is also called the tip. So the tail or the tip. One difference between a vector and a ray is that a ray, yes, it has an endpoint, and then on the other side where you have the arrow, it extends indefinitely, right? But that's not the case in the case of the vector. A vector has a very well-defined finite length, right? So it starts at one point, it ends at another point. The only purpose for the arrow is to say in which direction is pointing, right? So you have an initial point, you definitely have a terminal point. And the arrow, it gives direction, so obviously you can't mix up the initial and the terminal points, right? Because the arrow will have opposite direction. And can you imagine telling a pilot to go in a certain direction when you meant the opposite direction? Like it could have like huge ramifications, right? So this is where these things are used. All right, so the terminal point is called either the head or the tip. I don't like to use those because before, like, especially until we get used to them, when it's new, it's very easy to confuse tail and tip. So I just do initial point and terminal point. All right, notation for vectors. The vector can be denoted by its endpoints. You need two letters, point A, point B. So you could either say vector AB like this, and it's written A, B, the initial and the terminal point. And the arrow on top is a single-sided arrow like this. It's not a ray. Okay. You can also give the entire vector a lowercase symbol, A. So I can also call this vector A, just like that. Or in print, it's also bold A, but obviously we can't do that in handwriting, when we're handwriting. So when we're handwriting, it's either AB with an arrow like this or A with an arrow like that. And it makes a huge difference whether you put that arrow or not, because it becomes, a vector or a scalar based on whether or not you have the arrow. Okay. What does it mean to have a vector in standard position? You can have a free-floating vector anywhere in space, right? But the minute you take it, just like angles, when we talked about an angle, the minute you take an angle and you put the vertex at the origin, then it's in standard position, right? It's the same thing with a vector. The minute you take the vector and you anchor it so that the initial point is at the origin, then we say it's in standard position. And so now, here's a vector in standard position. The initial point is at the origin, right? And we can now figure out the magnitude and the direction of this vector. The direction of the vector is simply the angle between the x-axis and the vector going in, of course, the counterclockwise direction, because that's how we measure angles, right? So the direction of a vector is the angle between the vector and a horizontal line. So now, what do I mean by that? This vector happens to be in standard position because the initial point is at the origin. But what if you did have like a freestanding vector somewhere out in space? Then how would you measure the direction of that one? Well, what you do is you yourself draw a horizontal line at the initial point, and then when you measure that angle, that's the direction. Okay? So that's the direction. Now, if you have a vector pointing this way, right? You do the same thing. You draw a horizontal line at the initial side. And now, what would be angle 0? Here, right? So you measure the angle from what would constitute as angle 0. So like the horizontal going to the right, that's 0. And then you measure from that, and that is the angle. Okay, so instead of saying, okay, it's pointing downward and to the left, right? I could just say it has a measure of, 215 degrees, and I know exactly where it points, or it has a direction. Okay, yeah.
So what if it was it was still like facing upwards, but then it was how it's like it was facing that way, it still goes, it always goes from 0?
It always goes from 0. So like this one, let's say it has an angle of like 30 degrees, right? When it's pointing in the other direction, so sort of like it's in the second quadrant.
150.
Exactly.
So it never goes backwards.
No. Okay. Now, so that's the direction. What about the magnitude? The magnitude is a little bit more straightforward. It's straight up the distance. So if like the length of the arrow. So if I were to take a ruler and if I were to measure that blue arrow, however many centimeters or inches or whatever it is, that's the magnitude of it. So now, if a plane is, if a plane has a velocity vector of 710 miles an hour, am I going to draw a vector that's 710 units long? Obviously not. I scale things down. So in this diagram, the scale factor is that 1 centimeter is 5 feet per second. So if I were to take a ruler and if I were to measure this, it's 2.6 centimeters. If you measured this with a ruler, right? And so the magnitude of A is 5 times 2.6, 13 feet per second, right? It's just like if you were reading a map. Everybody okay with that? All right, a little bit more about notation. How do we denote magnitude? It's A in absolute value bars. So I say this is vector A, and then this is the magnitude of A is equal to 13 feet per second. So this is magnitude. Okay? Questions? Magnitude, right. So magnitude is just the numerical quantity without the direction. Yeah. Okay.
How do you denote the,
All right. So bearing is, okay. In the world of like in the nautical world, so in the world of like sailing and flying, right? Like you've seen in movies and stuff, you know, where they give the direction, right? And they're like, okay, we're flying at like, you know, 35 degrees or whatever. They have like their own way of measuring. And basically, it's called the bearing of a vector. And the bearing is, so we have what we call quadrant bearing. And instead of theta, they use the letter phi, which is another letter in the Greek alphabet. That gives you like the f sound. What that is a directional measurement between 0 and 90, east or west of the north-south line. So basically, take a look at this angle here. Traditionally, we would measure it starting with 0, and it would have what would be like it would have something like in the third quadrant, right? So what would the measure of that be? It'd be greater than 270 and between 360, right? But the way they measure it is they make the numerical value smaller. So they draw a north-south line, and then when you measure that, so if that's 145 on top, how much is that angle on the bottom? 35. So they say it's 35 degrees east of the south direction. You see what I'm talking about? And so they write it as south 35 east. Right? So that's what like the Navy might use. Okay? So I'm giving it to you for exposure. There may or may not be like some problems in the book that might like refer to that. Like just so when you see it, you know where they come from. You can refer it. And then a true bearing is a directional measurement where the angle is measured clockwise from north. Okay? So so if you have a vector like this, that's your vector. They would draw a vertical line, and if that's north, it's like clockwise from north. So this would be like 0-25 degrees. You always have like 3 numbers no matter what. Okay? Yeah. It'd be 045. Huh?
No. For the first bearing. Just say south.
Yeah, if it's 45 degrees, you still have to like specify a direction, right? Because like if it's, you mean if it's 45 degrees, like if it's like that, 45 degrees?
Yeah, could you ever say, is it always you start with
yeah, so if that was the angle and if this was 45, you would say north 45 east. 45 degrees east of north. Okay. Let's go. So here are some vectors. It's like somebody just like, threw up some vectors and they landed on the page wherever they would, right? And let's sort some vectors here. We have what we call parallel vectors. These have the same or opposite direction, but not necessarily the same magnitude. So here, vector A is parallel to vector B, and it's parallel to vector C, and what else? E and F, seemingly, right? Equivalent vectors have the same magnitude and direction. So what is equivalent here? Vector A is the same as what? Not B, but C. Not E, because E is in the opposite direction. So it has to be same magnitude and direction. Opposite vectors have the same magnitude but opposite direction. So C and E have the same size, but they're pointing in opposite direction. So we say E is the negative of A. And here the negative stands for direction. Okay? So in handwritten notation, it'll be E is the negative of angle A. That tells me that they have the same size, but they're going in opposite direction. So the negative does mean direction, meaning if I say my velocity is 30 miles an hour, and then if I say my velocity is negative 30 miles an hour, negative means I'm going in the opposite direction at 30 miles an hour. Yeah.
Can it be negative equals A?
It could be. It's just that they have opposite sign. Okay. So now, resultant vectors. Okay. We know how to add numbers, right? And so vectors, they don't add like numbers do. Like they add differently because vectors are not numbers like quantities. Like it's not like a 3 or a 5. So they have their own special way of adding. When we add two numbers, we get what we call a sum. When we add two vectors, the sum is called a resultant. So we say the resultant vector. There are two methods to find resultant vectors, and they're called the triangle method or the parallelogram method. I actually prefer the triangle method. So the way the triangle method works is this. You take your first vector, right, which is A, and you have to add it to vector B, right? So you take the first vector A. That vector starts on the left here and it ends on the right, okay? Now you put the second vector where the first one ended, right? So right here. But the way it has to be is you can't have two arrows touching each other. So it has to be arrow to end point, okay? So it's like one vector, another vector here, here. Now you have to make a third, now you have to connect them, and you have to go from the beginning of A to the end of B that way. Okay? So from the beginning of the first vector to the end of the second vector. Now, where to put the arrow? If these arrows represented the path that somebody was walking, right? And if they walked along A first, then they walked along B, you have to put the arrow in a direction that tells you where something started and where it ended. So if the person started at the beginning of A and then they walked and now they're at the end of B, your arrow has to go like this, meaning If you were to tell the whole story in short, you say they started at this point and they ended at that point. All right? And that green is what we call the sum of the two vectors. That's A plus B.
I thought you couldn't have two arrows attached.
You can have the resultant, you can, but not the arrows that you're adding. Okay? All right. So let's go and add these. So what you do is, it says to draw the resultant of each pair of vectors. So what I want you to do is we're just going to draw the resultant here. So what you do is, this is vector V, right? We're going to reproduce it as best as we can here. So same direction here. That's not the same direction, so it has to go like that, right? Do you see how that's V? I just want to make enough space to add the W on top. So that's vector V. Now, you take W and you have to add it as a continuation of this here. That's W, right? And then the resultant goes from the very beginning to the very end. Okay? All right. If you have enough space, you can like leave one of the arrows where they are and add the second one to the, like to the printed arrow, right? If you have enough space. All right. So look at this one here. I have A and I have negative A. So I'm going to use the blue one, and then I'm going to add the other one as, on top of that. So if the blue one ends to the right here, I need to add the red one from the beginning, so I need to add this red one on top of A. So how does that work? So this person walked along the blue, and then starting where they left off here, they have to walk along the red. So where are they going to go? Just straight back. And so now, where would the green arrow be from the very beginning of the blue to the end of the red? Where was the beginning of the blue? It was here. Where is the end of the red? It's the same point. So what's the resultant? 0. So we say A plus B is equal to 0.
You go from the beginning of the first one to the end of the second.
For the resultant, yes. Oh, sorry. I thought that was a... You do. So we're going to do A plus negative A equals 0. Okay, so take a look at this next one. I have two vectors here. One is 25 newtons north. That's going to be my vector A. And then 35 newtons south. That's going to be my vector B. So 25 newtons north, I'm going to represent that as being 25 newtons north. Let me draw that up here. Okay, so this is 25 newtons. And then I pick up where I left off, which is this, and I'm now going to go 35 newtons south. So I'm going to go in the south direction, 35 newtons. That's B. The resultant is from the beginning of A to the end of B. That's A plus B. Can we figure out how big that is? 10 newtons where? South. So A plus B is 10 newtons south. Right? You could also write it like 10 newtons south. So it's the resultant. You may be taking the difference of the numbers or you may not be. It's still called the resultant of the two vectors. All right? Okay. Next. Multiplying a vector by a scalar. So if if a vector is multiplied by a real number, then what happens is the vector just increases in size by that factor, right? So the vector increases in size okay, according to the factor. Now, if the scalar that you're multiplying the vector by is positive, so if k is positive, then the vector stays in the same direction. But if k is negative, then the vector gets opposite direction. So take a look here. I have vector A, and then I have vector 3a. And the only thing that happened is this was the size of vector A. It's now 3 times as big. All right? And because 3 is a positive number, then it stays in the same direction. So if I wanted to draw 2a, what would that look like? It would have twice the length, but go in the opposite direction. Oh, sorry, negative 2a. Huh? Okay? All right. So, you do. Normally, like, we don't like really highlight or that point. Here? Yeah. No, if it's a vector, it's understood that it stops there. Yeah. All right. So here it says I have x and I have y. I need to draw a schematic that shows 3 times x minus 3/4 of y. So 3 times x is just that x vector, but 3 times as big. So, we're going to make it 3 times as big. So that's 3x. Then I need 3/4 of y in the negative direction. So if y is that big, 3/4 of y is about that size, right? But what about negative 3/4 of y? It goes in the opposite direction here. And now it says if it says to draw 3x minus 3/4 y, you want the resultant of that, the sum or the difference. We don't subtract vectors. That concept doesn't exist. You don't ever subtract vectors. You can subtract numbers, but we don't subtract vectors. We only add vectors. It's just that one might be a negative, one might be a positive, right? But there's no such thing as subtracting vectors. There's no such thing as dividing vectors. There's no such thing as multiplying vectors. Those operations are operations that we use on numbers. They don't work on vectors because vectors are not numbers. They're different beings entirely. Okay? All right. So now what would the resultant look like here? Right. Ugh. Oh my gosh, I can't. It won't let me draw. Okay. It doesn't want me to draw the resultant. It might not be, it must not be allowed today. Let's see. Okay, so we were asked to draw 3x minus 3/4 y, right? The red vector, that's just 3x. The blue vector, that's just 3/4 y. What we have been asked to draw is really only the green vector, right? So the answer, 3x minus 3/4 y, is that green vector. So theoretically, you know, the red and the blue could not even be there, right? All you need is that green vector. But of course, if you draw it, you're going to draw the whole triangle. Yeah.
On a test, if you just do the green.
Yeah, no. Because I need to know where it comes from. You can't just draw a random line and say here, right? Okay. Good try, though. Try again. Okay. Now, vector components. Vectors which add to create R are called the components of R. So here I have my green vector. Where did it come from? It was created out of the addition of the red and the blue. So the red and the blue are components of the green vector R. Now, I can draw a vector and call it R, and I can draw components to this vector, and there are many, many choices. There is an infinite number of vectors I can draw as components of this vector. So basically, I could say that and that are components of that vector, right? Sure. I could say this and this, oh my gosh, are components of that vector. Okay? I could even say this and this are components of that vector. Okay? Now, I can also be not as bold and say, okay, this and this are components of that vector, and make it a 90-degree angle in between. Right? I'm legally allowed to do that. So I have drawn 3 pairs of components for this note. 1, 2, 3 here, and another one. 4 pairs of components to this. They're all components. These 2, however, the last ones I drew, because there is a horizontal and a vertical one, these are called rectangular components. Right? This is horizontal and vertical. The rectangular components, you can imagine, because there is that coveted 90-degree angle there, are the most widely used components, right? That's what, when we say draw the components of a vector, we are usually talking about the rectangular components, because now that there is a 90-degree angle there and it's a right triangle, man, I could do so much, right? Yeah, this is why we do trig before chapter 8 and not after. Okay, so here's the deal. I hate to break it to you, but the whole sine, cosine, tangent business is something that you will never be able to really escape from. So, person, Will, is digging in his garden. And when you least expect it, when you're doing the most relaxing thing ever, right? Gardening, here we go. The trig just pops up out of the earth at you. So, while digging in his garden, Will pushes a shovel into the ground with a force of 630 newtons at an angle of 70 degrees with the ground. Usual. Okay, nothing big here. Now we're asked to draw a diagram that shows the resolution of the force that Will exerts into its rectangular components. Okay, so this series of this phrase, it's kind of a broken phrase, the resolution of the force into its rectangular components. So often we don't say draw the rectangular components, we say resolve this vector into its rectangular components. So let's first draw like a picture. So I always stress in math the difference between a picture and a mathematical diagram, right? Like here, there is another picture, but that's not a diagram. So here is a picture. This is the ground. And here is that shovel. And, you know, Will could really be like standing in whatever direction. That's the best I could do to draw a shovel. Okay? The shovel has an angle of 70 degrees with the ground. That shovel, right? So how is Will applying force into the ground? He's applying force into the ground through the shovel, right? So his force vector is directed along the shovel into the ground, right? So this shovel is what the force vector is being applied through. So we can say that that's the force, and it's got 630 newtons. So that's that's Will. All right. So now let's draw that here. Let's draw the diagram. So this is the force vector, and it's 630 newtons. And now we want to draw a diagram that resolves this into its rectangular components. So what we do is, from here, we're going to draw 2 arrows. Basically, we want to complete this right triangle. So here is a line, and then here is another line. And now, how to place the arrows? How to place the arrows? Think of it this way. The force is going from Will into the ground. So, if you followed the purple vector, or if you followed the green and the blue, both situations have to show the force going from Will into the ground. So, from Will into the ground, that means here, from Will into the ground and over here. So there is no discrepancy on how to draw those arrows, right? This is the only way to draw the arrows so that it goes from Will to the tip of the shovel. Okay? So now those are the rectangular components, but we got to label them. That's a 90-degree angle. This horizontal one, because it's lying in the x direction, I call it the x component, and I call this the y component. And now, this is a complete diagram. If any of these component parts are missing, I can't give you full credit. So if you don't have the x, if you don't have the y, if you don't have the arrows, I can't give you full credit here. Okay, now find the magnitudes of the horizontal and vertical components. Magnitude is just size, length. So if this is a right triangle, and if the hypotenuse is 630, surely I can find, say it, what's it called? Sine or cosine, because what else do I know? I know that this angle is 70 degrees. Okay? Yup. So let's do the x component first. Cosine of 70 is equal to what? X over 630. X arrow. So the x component is equal to 630 cosine of 70. And how much is that? $215.215. Okay, let's do 215.5 newtons. Now, for the y component, sine of 70 is equal to y over 630. So how much is that? So y is 630 sine of 70. What is it? So 0.0 newtons. So that means there is 592 newtons of force being applied vertically down. There is 215 being horizontally applied. Okay? Together they combine for that angular 630 newtons. Okay. All right, let's do another one. A player kicks a soccer ball so that it leaves the ground with a velocity of 44 feet per second at an angle of 33 degrees with the ground. Okay? All right. So he kicks this ball, right? When he kicks it like that, what happens to the ball? Not only does it have an elevation now, not only does it go above the ground, it also goes quite a ways across the field, right? So when he kicks it, he gives it a vertical velocity, which makes it go up, and he gives it a horizontal velocity, which makes it go forward. We don't know this when we're watching soccer, and like you see the ball going from like one end of the court to the other, or the field to the other end of the field. We don't know, but like the horizontal velocity is acting independently of the vertical velocity, right? Like they don't have anything to do with each other. So let's draw a diagram. Again, this is a picture. We need a diagram. So here's the vector. Here is the velocity vector. We're going to call the vector v, and it's 44 feet per second. And now I need to draw the components. So here I have x, and here I have y in red. And now the arrows. This is the direction of the ball. So whether I follow the purple arrow, all right, the ball starts here and ends at the at the head of the arrow. Or if I were to follow the blue and the red, it would have to begin and end in the same place. So again, there is only one way to draw the arrows so that both situations start and end at the same place. So now, this is y, this is x. Oh, I forgot one thing. I'll go back to the other one. And here I have to say 33 degrees. Okay? Okay. Here, because we were I have wrong notation up here. Because we have, we're looking for the magnitude, these should all have magnitude symbols, because otherwise it's extremely wrong. Okay? So that's the x vector, that's the y vector. No arrows, no absolute value, like magnitude symbols needed on the diagram. But in my work, because I'm looking for magnitude, I need to have the absolute value symbol, the bars. Okay, so let's find the magnitude. Let's do x first. Cosine of 33 is equal to magnitude of x over 44. So magnitude of x is 44. Cosine 33.
Do we always need to put the absolute?
Always. Whenever you're looking for magnitude, you've got to, huh? It can be negative. Okay, so that's the thing. No, the speed cannot be negative. Let me finish this and then I'll talk about that. That's actually like a whole thing. So how much is this? 44 cosine 33? 36.9. And it's feet per second. And then sine of 33 is equal to y over 44. So magnitude of y is 44 sine 33. And how much is that? Okay, now, talking about speed. Speed cannot be negative. Because when you say there is, it's negative 30 miles an hour, the speed is 30. The negative means it's going in the negative direction, right? So the negative is direction. Now, so look at this one. The horizontal velocity is 36.9. The vertical velocity is 23.9, meaning the horizontal velocity is higher, right? So if you watch the trajectory of that ball, it's going to go further in the horizontal direction than it will, high up, right? Okay, now, one other thing I want to talk about. Take a look here. When we simplified the x component, what did we get? What was 630? That was the size of the vector that we were resolving in the one. So we got the vector, the original vector, cosine of the angle, right? So it's the vector. So x was the vector times cosine of the angle. What was it here? The vector times the cosine of the angle. Hey, that must be a trend or something. What did we get for the y component here? The vector times the sine of the angle. And what did we get here for the y? The vector times the sine of the angle. Hey, that must be something. Hey, I wonder if that's the reason why in chapter 4 I kept saying sine is always the vertical side and cosine is always the horizontal side. Because in vectors, the cosine is always the horizontal component and the sine is always the vertical component. And you see now, whether you're in chapter 4 or 8 or 9 or whatever, math stays consistent. Whether it's August or January or March later on, the math of it will be consistent no matter what you do, right? So the homework for next time will be this. And